Okay, in this video we're going to walk through how to use the USGS Rational Method for determining flow values, Q values, for a watershed. So this project is in Oklahoma, and so we're basing this off of the Oklahoma Department of Transportation Roadway Drainage Manual, specifically Chapter 7, which covers hydrology, is what this will be based out of. And the project we're just looking at a small watershed that is a small enough area that we want to, we know we need to use the rational method, and that's based on the typical ODOT methods. Here it talks about basically the size of the watershed area, and we determined our watershed, I think, is around 30 acres or so, and it doesn't include stream flow. So we're going to use the rational method. So if we scroll down within this hydrologic manual, and this will basically be looking through section 7.6, the rational method. Again, it's estimating storm peak runoff for areas up to 640 acres, but works really best below 200 acres. So let's take a look at the equation for the rational method. So our runoff value is going to be Q, and then there's four other factors here. So CF, C, I, and A, and it works through. So Q is our cubic feet per second rate of runoff, and then we look, C here is a runoff coefficient, and it's going to be a constant, and we'll go through, but there's a figure basically that you can pick that value straight out of, and that's based off of kind of the landscape around and how fast water would typically flow across that landscape. The CF is a constant, but it's a multiplier based on the year flow that you're looking at. So here it's just 1 for the 10-year or less recurrence interval, and then it just kind of scales up just a little bit for each one. I is the average rainfall intensity, and this is kind of the bulk of this equation, and this is the workhorse of the equation, and it takes a lot more to calculate. We'll kind of come back to that in a little bit. A here is the drainage area of the watershed, just in acres. So that's a pretty simple constant that we can easily identify. So it seems it's a fairly simple equation, and for the most part it is, but there's multiple steps to work through. So in the previous video, I'll pull up Civil 3D here, we had gone through and we worked through bringing in contours, and we manually delineated this watershed here, this polygon here. It's actually a closed polyline feature. And so we determined, based on the properties of this, so it was about the area here, this is in square feet, so about 1.5 million square feet, which I believe came out to be about 33 acres. So, and then again we came in and we determined the length of the flow line, which was 1,390 feet. So this is all based on Civil 3D, and we got a high point elevation and a low point elevation, and I'll kind of go in a minute and explain why that's needed. But this is what we're basing this off of, this small watershed, pretty much looking at flows to this intersection in view of trying to size a pipe to go underneath the intersection. Okay, so now we'll come back to the equation a little bit, and one thing I've done just previously, I've worked up an Excel spreadsheet that we'll kind of walk through, that'll help us put in these values and work through this equation. But let's just take a look at the actual equation itself and what goes into it. Again, we've already looked through basically the bulk of this equation. CF is just purely a constant multiplier here. C we'll get to in just a second, and A is the area in acres of our watershed, which we said was about 33 acres. So let's scroll down and let's take a look at C. So here it talks about the runoff coefficient, and this kind of jumps around quite a bit, this manual, so it's kind of hard to get to where you need to go. But if we come down, this is page, I believe, 7.6-6, but figure 7.6-A is the runoff coefficients for the rational equation. So it goes through all the different kind of landscape types and gives you a range for runoff coefficients. And so if you have a big, really diverse area, you would probably need to break it up into chunks and decide how much of it is each of these type of land use area. If we go back to kind of view the aerial imagery of our watershed, we're basically looking at just open pasture land. So it pretty much is that for the whole thing. There's a few trees, but it's not a thick wooded area. It's not that big of a contributing factor. So we want to go through and look and try to find something that resembles what we're looking at. So we have a pasture land equation here. And so it breaks it down between heavy soils and sandy soils. This area is kind of a river bottom, kind of bottomland area. And so I would imagine the soils are somewhat sandy, silty area. It's not just a hard, deep clay. So we're probably going to look more on the sandy soil side, but not super sandy. And you can see how these ranges actually overlap between the two. So we'll probably kind of pick a value, let's just say a 0.2, that kind of gets to the upper end of the sandy soil and the lower end of the heavy soil. And so that'll give us our C value. So now, primarily what we're looking at is the I value. And if you flip through here, it's actually kind of hard to find the actual equation for the I value. But if we scroll down on, excuse all the page down, but if we look through, I think it's on this page here. So there's a big table here. It's figure 7.6-P on page 7.6-21. So you have the curve coefficients for this equation. So this is your I equation, and it has constants A, B, and C, which we'll pull from this table, and we'll talk about that in a second, and then T of C, which is the time of concentration. And that's kind of the big thing we'll need to calculate here. So if we look, so A, B, and C, within this table, it has zones, and these are different zones within the state of Oklahoma based on precipitation regimes and average annual precipitation values. And it gives values for A, B, and C depending on the storm return interval that we're looking at. So I believe this project is in zone 2. So we'll be looking here, and I believe, let's scroll up a little bit. Okay, so this is a map of the state of Oklahoma. I think this is page, let's see, 7.6-12, and it breaks it into all the different zones. So I think we're looking in Muskogee County, so we're in zone 2. So we'll come back to that in a little bit, but those are where we'll derive those constants from. And we'll talk about there's another method of calculating that as well, but we'll get to that here in just a little bit. So time of concentration is actually the main thing we're looking for when we're calculating our Q values. So again, this manual kind of jumps around quite a bit, so forgive all the back and forth here. So here in section 7.6.6 is the equation for the time of concentration. And the total time of concentration is broken up into two factors, the overland flow time and the time for channel flow. So T of O for overland flow and T of F for channel or gutter flow. This project, like most for small little watersheds like this, generally it's a flat kind of overland area, and so it's almost 100% sheet flow. If we had gotten to a point here that there had this area had eroded out quite a bit, there was a little gully that came through here, that type of area would probably lend itself more to channel flow. So you could have sheet flow coming across it, but then it hit this gutter and flowed into here. We don't have that. I'll kind of discuss what that is, but for the most part, we can ignore the T of F. So we'll look at overland flow. So that's going to be essentially what we're calculating. So this equation, don't get scared off by it. It's fairly simple. We have a K, which is a constant value, and it's similar to our C value we created before, and it's based on the surface type for ground cover. And it has a table right here on this page right below it to pick your K value. So again, we were looking at just pasture land, and so we can come in here in our average pasture, and so the K value is 1.04. So we'll just kind of note that, and so we've already gotten our K value here. So we have two other factors here. The L sub 0 is length of overland flow, and the S sub 0 or O is the slope of the overland flow path. So we measured our length of overland flow path directly from our Civil 3D object, and it was about 1390 feet. Our slope, which for this project and for most of these projects, it's a fairly even slope that goes throughout the area. And so for that, we can just basically get the high point elevation and the low point elevation, and then just divide that out by the length of the path to get our slope value. If you have an area where it's very different terrain over the course of the flow path, you would probably need to divide that out into different areas of slope, which the manual actually goes into detailing how to do that, but then have a weighted average for that slope value. Here we're just going to do it very simply and just take high-low elevation divided by length. And that's really all it is to calculating this T of 0. For channel flow, it's basically the exact same type equation. You have a K value, a length, and a slope value, but this is purely for the area of the channel flow, and a separate K for the type of basically channel you're looking at. And that's why this is K prime, which is different from K. But then the length just purely of the channel and the slope of the channel. So for our purposes, we don't have any channel flow, so this will all just be 0. And what we're looking at is just T of 0. So I have an Excel spreadsheet already created here, but basically it's just kind of to aid in doing the calculations. You can do all of these by hand. But basically I have a drainage structure ID, and then each of the areas I need to fill in. These areas in blue are basically things that automatically fill in, and then the areas left blank are things that I need to actually physically put in. So if we remember, for this watershed, we have a total drainage area of 33 acres. And we determined the runoff factor, the C value, was 0.2. And our K for the pasture land was 1.04. Our length of the channel or the flow path was 1,390 feet. Our high elevation, let me take a look, was 573 feet, and our low elevation was 545. And so now you can see these cells in blue automatically working in, and so basically this one, I put these, so the length will obviously need for the calculation, and then the high and low elevation are purely to derive the slope. And again, one thing to note, the slope is calculated in feet over feet, not percent slope. I know it's kind of confusing based on the manual which one they're looking for, but it is feet over feet. So again, that just derives that from this information. And then this cell for t of 0, this is the goofy Excel formula, but basically it works through what is listed here. For the channel or street or flow, gutter flow, this is all going to be zeros because we don't have any of this, so this will calculate to 0. And in here, basically the total time of concentration, which adds the overland in the channel flow, is here. And because obviously the channel flow is 0, it just equals our overland flow. So now once we put this in, I have a separate sheet here for the Q values, just to kind of separate these two steps. And here, this will just automatically bring in a lot of this information. So now we have our drainage area, which is our A value, again our runoff factor, which is C, and now we have our time of concentration. And again, now this dumps into this big formula for I. And so what I've done, again, I've added these values for zone 2. And so I have an I value for the 2-year return interval, 5-year, 10, 25, and 50, and 100-year return intervals. And so these equations down here basically are calculating the I value. And so it's taking this time of concentration versus the specific A, B, and C values for each return interval, and now calculating the I. And so now we can come in and these will automatically calculate the Q values. So it takes into account the C, which is here, the I, which we calculated here using our time of concentration here, and the A value. And then the C of F is incorporated within this formula. So remember that the C of F was 1 for everything the 10-year flow and under. So you don't see that calculated in here because it would just equal itself. But once we get to the 25-year, we now have this multiplier, the 1.1. And similarly for the 50 and 100-year, we have that extra value. So that's pretty much how to use the rational method. You know, the spreadsheet obviously is something I created myself, but it helps kind of outline the two separate processes that you need to work through to calculate the actual time of concentration, and then come back in, calculate your I values based on the time of concentration, and then use all of that information to calculate your Q values. So I hope this has been helpful, and that's pretty much it. Thanks.